Hey everyone, welcome back. Today we're diving into a research paper from UC Berkeley, published at NeurIPS 2025, that asks a surprisingly simple but important question. Why do multi-agent AI systems fail? The answers they found are both fascinating and alarming. Despite all the hype around multi-agent AI, these systems fail at rates between 41 and 87% on standard benchmarks. That's not a small bug. That's a fundamental, widespread challenge the AI community hasn't fully cracked yet. Let's start with the big picture. Multi-agent LLM systems, or MAS for short, are groups of AI agents that collaborate to complete complex tasks. Think of it like a company, with a manager agent, specialist agents, and reviewer agents all working together. Examples include ChatDev, which simulates a software engineering team, and MetaGPT, which mimics a tech company's entire workflow. These systems are powerful in theory, but in practice, they fail a lot. The problem is that until now, we haven't had a principled way to understand why. Most prior research focused on making individual agents smarter, better memory, better reasoning, better tools. But no one had systematically mapped out the failure patterns. This paper sets out to fix that. The research team's main contribution is MAST, the Multi-Agent System Failure Taxonomy. They started by collecting execution traces from 7 popular open-source MAST frameworks. They analyzed these traces using a rigorous qualitative method called grounded theory, which means they didn't start with predetermined categories. Instead, they let the patterns emerge organically from the data. The result is MAST data, a dataset of 1,642 annotated execution traces from 7 frameworks. Human experts annotated these traces, going through over 10 hours of annotation per person, and achieved a very strong inter-annotator agreement score of 0.88 on the Cohen's-Kappa scale. That's considered excellent agreement. So what did they find? The taxonomy identifies 14 distinct failure modes, organized into 3 main categories. These are system design issues, inter-agent misalignment, and task verification failures. Let's go through each one. The first category is system design issues, which accounts for a whopping 44.2% of all failures. These are problems baked into how the system is architected and how agents are instructed. The most common failure here is step repetition. Agents getting stuck in loops and repeating the same actions over and over. Another major issue is being unaware of termination conditions, where agents keep running indefinitely because they don't know when to stop. There's also failing to follow task specifications, losing conversation history between turns, and disobeying assigned role constraints. The second category is inter-agent misalignment, covering 32.3% of failures. This is about breakdowns in communication and coordination between agents. The biggest failure mode here is reasoning action mismatch. An agent thinks one thing, but does something completely different. Others include task derailment, failure to ask for clarification, and conversation resets. Here's a vivid example from the paper. A phone agent knew the correct username format for a login, but failed to communicate that information to the supervisor agent. The supervisor kept trying wrong credentials, the login kept failing, and the whole task collapsed. Not because any agent was stupid, but because they didn't coordinate their information. The third category is task verification, accounting for 23.5% of failures. This is about whether agents properly check their own outputs. The research found that agents commonly make only superficial checks, like confirming that code compiles, but not testing whether the program actually works correctly. For example, a chess program passed compilation checks, but contained bugs in the actual game rules. It looked fine on the surface but was completely broken underneath. The core problem is that current verification steps are shallow and single-stage. Next, let's look at the 3 key insights discovered in this research. Here's the first critical insight from the research. Most people assume MAS failures happen because the underlying AI model isn't capable enough. But the paper demonstrates this is not the whole story. Using the exact same model, GPT-4o, the researchers improved ChatDev's task success rate by 9.4%, simply by adjusting how agents coordinate with each other. The model didn't change. The system design did. This means a large fraction of failures are architectural problems, not fundamental model limitations. The second key insight is about communication. You might think that giving agents more context or improving message formats would fix misalignment failures. But the paper argues this is insufficient. The real problem is what they call a failure of social reasoning. Agents cannot model each other's informational needs. They can't infer what a teammate knows or doesn't know. Solving this requires more than better prompts. It requires advances in how agents fundamentally model and reason about each other. The third insight is about verification. Single-stage, low-level checking is not enough. Robust multi-agent systems need multi-level verification, checking both low-level correctness like syntax and compilation, and high-level objectives like whether the output actually achieves the user's goal. When the researchers added a high-level task objective verification step to ChatDev, success rates improved by 15.6%. That's an enormous gain from a single structural change. Now let's look at how failures are distributed across different systems. When you look at the 6 systems tested, the failure rates are striking. AppWorld had the highest failure rate at 86.7%, HyperAgent at 74.7%, ChatDev was at 66.7%. Even the best-performing system, AG2, still failed 41% of the time. These aren't edge cases. These are systematic, widespread problems. To enable the research community to study these failures at scale, the team also built an LLM as a judge pipeline using OpenAI's O1 model. With few-shot examples, this automated annotator achieved 94% accuracy against human labels and a Cohen's kappa agreement of 0.77. This means MAST isn't just a research taxonomy, it's a practical tool that can be automatically applied to any MAST framework using the agent-python library. So what does all this mean for building better multi-agent systems? The paper's most important message is that MAST failures are fundamentally about system design, not model capability. It's like organizational theory. Even a team of brilliant people will fail if the organizational structure is broken. The researchers draw a direct parallel to high-reliability organizations in fields like aviation and medicine, where careful system design prevents catastrophic failures even when individual components are imperfect. For practitioners, 3 actionable lessons emerge. First, design your agent roles and task specifications explicitly. Don't assume agents will naturally understand their responsibilities. Second, build communication protocols that force agents to share and verify information before acting on assumptions. And third, implement multi-level verification that checks both the mechanics of execution and whether the final output genuinely achieves the intended goal. MAST and MAST data are open-sourced on GitHub and Hugging Face. The researchers hope this taxonomy serves as a foundational framework for diagnosing, debugging, and ultimately redesigning multi-agent systems to be far more reliable than they are today. If you want to go deeper, check out the paper on arXiv, link in the description. That's it for today. See you in the next one.